Okay, good afternoon. Uh, so let me introduce today's speaker, Raktim Abir. We did almost same time PhD.
Yes.
Yeah. Okay. So he is now in Aligarh Muslim University, and he's one of the experts on small x physics and
Okay.
like EIC related
So this is for up down.
field, theoretical side.
Side.
So you just enjoy his talk, and after his talk, you can talk to him to know more about in that direction. Okay. Thank you, Abir. Please.
Okay, so before I start, I like to thank the organizers for inviting me here for this talk, and it's a pleasure to be here in this beautiful and unique campus of ICTS. Um, so so this talk has a broadly defined 4 segments. In the very beginning, I'll be giving a very quick review on things like density matrix, qubits, pure mixed states, separable entangled states, measures of entanglement, etc. And then we'll go back a bit in history, and then we'll have a discussion on um, one old question on the foundation of quantum mechanics, whether quantum mechanics is incomplete, followed by some discussion on non-locality of quantum mechanics, Bell's inequality, CH-SH inequality, and then we'll have a review on how this Bell test or Bell inequality test can be performed in a high energy collider setup, say in LHC or say for that matter EIC. And at the end, I'll be trying to give some preliminary comments on how to connect this study with the traditional study of PDFs, GPDs, TMDs, and also some remarks on what happened to NLO, and can we say something on the decoherence. So that is my pretty much plan. So to start with the density matrix, density matrix is something that was introduced by Newman in 1927, and density matrix is something that that represent a quantum state. But then wave function is also something that represent quantum state. Both wave function and density matrix represent quantum states, but they differ in scope and generality. While wave function or say a state vector in a Hilbert space, they represent what we call the pure state. Density matrix represent both pure and mixed states. And these density matrices are constructed from the projections of all available states of that ensemble, associated ensemble. Likewise, this mixed state also are kind of statistical ensemble of pure state. They are convex sum of pure states. And these mixed states often arise in the context of open quantum system discussions. So this density matrix is Hermitian. Probably many of us already know these things. And they are what we call this positive semi-definite Hermitian operators with trace 1. And if the Hilbert space having dimension n, then we require n square minus 1 number of real parameter to fully characterize the density matrix. And whenever we need to have some kind of expectation value of the observable, we can see that this is the product trace. moving on to qubits. Qubits or quantum bits are again kind of two-level system, and unlike so these qubits, we all know that these are the basic ingredients of quantum computation and quantum information science. Now, unlike the classical bits, which are just like 0 and 1, qubits are like superposition of 0 and 1 state. It's like basically it's for in our language, it's two-level system. While this two-level system, two-level problem is an old problem in quantum mechanics, this particular phase qubit is a relatively new. It first appeared in 1995. So these are the few examples. The first very useful and popular example is, of course, spin up and spin down for a spin half particle, and then photon polarization, and then we have this exotic trapped ion and superconducting qubits. So what is the density matrix of a qubit? The density matrix of a qubit, of course, is more simpler, and we can see that this is I2 is 2 cross 2 matrix, and sigma is Pauli matrices. So basically, density matrix of a qubit requires just 3 parameters, because the Hilbert space is 2 dimension. It's we require 3 parameters to fully characterize a qubit, density matrix of a qubit. Now, complexity arises when we have more than one single qubit. Say we have 2 qubit and they are correlated quantum, there are quantum correlation between them. So they comprise a single system with 2 qubit. So now the Hilbert space is kind of bipartite, and obviously the density matrix is now more bigger, and we can start counting the number of parameters it requires. It requires 15 parameters. So 3 here, 3 here, and 9 here. And this C matrix is what we call the correlation matrix. It's a 3 cross 3 matrix, and it encodes pretty much the maximum information that the density matrix carrying. Now, question is, what is a separable state? So this is 2 qubit system. So the full system is 2 qubit, and individual qubit I can think of that like subsystem of the full system. Now, how can I can tell that this system is entangled or separable? So I can say that if the quantum state is separable, if and only if the density matrix can be written as a convex sum of the product of density matrix of the individual subsystems. And convex sums is a kind of weighted sum where the weights are the probabilities. But if we can't able to write this way, then the system is entangled. So that is pretty much the definition of separable state and entangled state. So a quantum system, two quantum system are entangled if the joint state cannot be written as a product of the individual state. And the example, the most famous probably the example is of course the EPR spin states. So this is a 2 qubit state where this red arrows correspond to the first qubit spins and the blue arrows are the second qubit spins. Now this full state can't be written as a tensor product of the two individual qubits, and that makes it the entangled. And this also shows a kind of perfect anti-correlation. If we pay little attention here, that we have 2 qubit and this is their joint state. Now, if I measure the first qubit, spin of the first qubit along the z-axis, I get some outcome. This outcome could be either plus half or minus half. But the moment I have done that measurement, the outcome of the measurement of the second qubit is immediately settled. if I am getting, after measuring the first qubit plus half, the measurement of the second qubit is not at all required. We already know that second qubit is at the minus half because they have this perfect anti-correlation, and vice versa. So this makes the whole thing not just entangled, it's also gives make it maximally entangled, because the outcome of the measurement of the first qubit give me certainty in predicting the outcome of the measurement of the second qubit. This 100% certainty makes it maximally entangled. If we can, based on the measurement of the first qubit, if we can prescribe some probability of outcome in the second qubit, then we'll say that it's entangled but may not be maximally entangled. And if we can't say anything, then it is separable. So, how to quantify this entanglement? So there are entanglement measures. These measures are like a marker, not just marker, it's like give the strength of the entanglement. So these measures are mostly zero, all of them, zero when the states are separable, and they saturate to unity when we have the maximally entangled state. So the first most popular measure is of course the entangled entropy, where we basically take the entanglement of the one of the subsystem, and then we have concurrence. Concurrence C made up of the eigenvalues of this particular object, ordered eigenvalue. So lambda 1 is the largest, and then we also have this entanglement negativity, and this negativity is another measure. So based on different situation, some measures are more convenient than the other, and this particular entanglement negativity based on this what we call the Perez-Horodecky positive partial transpose criteria. And then there is this fourth one, entanglement of formation. This is often used for the mixed state, and if we have just two qubit like the one we are discussing here, this is there is a direct connection between these two. Oh, this one.
Double mod of P. Yeah.
Oh, so what it would require little bit of discussion. So rho is a yeah. So so you can see this rho is the density matrix of the composite system, and this composite system had two subsystem, A and B. Now this is the this is a transpose of the S subsystem. So that's why it's called the partial transpose of the density matrix. So what we do, we will not going to transpose the entire row, but we will just transpose the B part of that density matrix. Once we have done that, then we'll see that what are the eigenvalues of that partially transposed density matrix. Take the mod of that -1 divided by 2. So we'll see if, so let me just explain what is that. It is Horodecky partial transpose criteria. It says that if I able to make a partial transpose of density matrix, then try to find the eigenvalues. If I find a single negative eigenvalue, then that will say that the system is entangled. So that is the criteria, and based on that criteria, I have this measure negativity.
It's the A part.
So this is called, so it is transposing the one of the subsystem, keeping the other subsystem intact. This is called.
Get the row, I mean, after tracing A or right?
After tracing one of the qubit. That is why it is called partial transpose. Once that is done, then we look for the eigenvalues. If one of the eigenvalues is negative, then the system is.
How will you get the, I mean, because they are entangled.
So you write down the matrix and then you transpose the half of the so that it's a technique that maybe I can show in the board. So this is the same as this, but for the because it's a mixed state, we have several such. Okay.
So after doing this partial transpose, what you see, double mod means what?
Double mod means you take the magnitude of those things. Just to check if there is a negative, there is one or more than one negative eigenvalue of that partially transposed density matrix, and if yes, take their square and see how much it is differing from that. All of them are positive. So presence of a negative eigenvalue in the partially transposed density matrix is a sufficient condition for to have the entanglement in 2 cross 2 and 2 cross 3 system, and if it is more than that, then it is a necessary condition.
Still, I didn't get what number will you put there? I mean, it's a number, right?
It's a number. This number runs from 0 to 1. No, 4. For this case, 4.
Traced out, right?
No. In this case, 4. All of them are 4 cross 4.
Okay. I'm sorry.
No, that's okay. Any other question? It's a good point to ask question because this is pretty much the conclusion of the first part of my talk. Okay, so let's move on and go little bit in history, and we'll have a little quick discussion on that question of completeness of quantum mechanics. Okay, so quantum mechanics in its heart is a probabilistic theory. It's like a statistical theory, and which is a kind of in contrary to the Newtonian mechanics or relativity, where the things can be predicted given we have sufficient knowledge of the initial conditions and mechanisms, and then the prediction can be done with certainty. So that is a qualitative difference that we have with quantum mechanics and other like classical mechanics. Now, we just saw that if there is entanglement, we can predict the outcome of the second qubit with certainty. So that was a kind of situation that triggered some discussion long back. Einstein and other, they wrote this famous EPR paper in 1935. So this certainty of outcome in the case of this entanglement and the probabilistic nature of quantum mechanics, which is like a dichotomy, and that triggered this paper, these arguments by Einstein and others, and they said that if, so this is very important, let's spend some time. If we have we can predict a physical quantity with certainty without disturbing the system, then there exists an element of reality corresponding to that quantity. So if we can able to predict something without disturbing something, so that says that there are properties inherent in that object which was there even before the measurement was done. So that is a piece of element of reality attached with that object. But if that is true, then why quantum mechanics is probabilistic? So perhaps, according to their argument, perhaps we haven't accessed all all the variables of the theory. There are few variables which are yet not accessible to us or hidden from us, and they call it that hidden variables. Because they are not yet accessible or hidden, that's why the theory appears to be probabilistic. Once we have access to those variables, then the outcome of the quantum mechanics can be predicted with certainty. And that leads to what is called this hidden variable theory. Now, in the same year, Schrodinger put a rejoinder to this paper after a few months. And in that that paper, he argued that no, this entanglement or the kind of certainty in prediction it is giving to us is actually a characteristic feature of quantum mechanics. So that triggered this long debate of, so this is a quotation from this paper, actually it's like a screenshot. And here I have my most favorite line of that in that paper. The best possible knowledge of a whole does not necessarily include the best possible knowledge of all its part. So the real question was whether we have this hidden variable and whether the quantum mechanics is incomplete because we don't have this access to these variables, or quantum mechanics in its core is a non-local and inherently probabilistic. So that this was the like major step towards this solving this question was in 1964 by John Bell. So in 1964 he proposed some, like he gave the argument why the quantum mechanics are actually the non-local and non-local theory. So let's move on to that. So after Bell, there was this, yes. I'll tell you in detail. So non-local, I'll tell you just now. So after a few years, this CHSH inequality came. So CHSH inequality is more general inequality and it is better suited for the experiment also. So what is that? Let me spend some little time on that. Then we will address that. What is non-locality? So we can simply understood this in this setup where we have these two boxes. What is there in the boxes not important at the moment, but what we can just understand that we have these two boxes, and these two boxes can take the inputs, binary inputs. So both of them can take the input and they also deliver output. So in the input, they can take binaries. That means either they can take 0 or 1. So whether they will take 0 or 1, that would be decided by a, say, random number generator. So for box A, we have a random number generator that will tell whether we should take the 0 or 1 as a input. Here also there is a random number generator and it would say whether we take 0 and 1. And this input 0 or 1 will trigger something inside and it will deliver either plus or minus. That's the idea. Now, now the test concerned the correlation between the output values generated within the same trial. So if I keep repeating these experiments and making these two boxes causally disconnected, so they are space-like separated. No influence no influence of box A can influence box B during the trial or during the measurement. If we ensure these conditions, then we can have a correlation of the outcome outcome, and then we can also define some kind of like parameter from the correlation of the outcome. And if the input values are truly random and boxes are this is causally spatially not spatially spatially separated, so that the locality prevents the communication between the boxes during trial, then the following inequality holds. So this inequality would say that if the if the boxes are space-like separated and this is happening truly randomly, then under the condition of locality and realism, this should be less than or less than 2 or equals to. So there is this two condition. One is reality and other is local. Reality means that I just mentioned, that reality means the properties of the element or object is already there before we measure something. And locality means that they are locality in the sense that any influence require any influence can't move faster than the velocity of light. So that is pretty much the locality. Okay, so under this condition, the discovery of the Bell is that any theory of physics that is both local, which is physically influenced, do not propagate faster than the light, and realistic, that is physical properties are defined before and independent of the observation, which is not true for the quantum mechanics. Now we understand. Those correlation are bounded more strongly than the quantum theory. So quantum theory says that this inequality could be there, but it is not true, more than 2. And if it is local and realism, then it is strictly true. So we have now something that can actually help having some experiment decide on that old problem. Okay. All right. All right. So 0, 0 is 0, 0 are the inputs, input binary. So either the first qubit have 0 as input and second qubit have 0 as input, even though these inputs are totally independent. And this x and y are the output. So x is the output of the first qubit when the input was 0, y is the output of the second qubit when the input was 0. Okay, so let's now place this problem in our familiar spin cases. So now we can think of these two boxes as having the like 2 qubit. So or even in our language, let's have 2 particle in either of the boxes, spin half particle. So this is the first qubit and this is the second qubit. So now what is the idea? Idea is that we will measure the spins of these particles, particle A and so qubit A and qubit B, but we have these 2 axes of measurement of the spins. Here we have this Z axis and X axis. So likewise in the previously the input was 0 or 1. So if it is 0, then we will measure on the along the Z axis. If it is 1, then it will measure along the X axis. And we will not decide that, the random number will decide that. Likewise, we have here qubit B, here also we have binary input 0 and 1. Say for 0 we will measure along this way and for 1 along this way. Okay, and these two qubits are prepared in an entangled state, in this state. And then we will try to see what happened. What would be the value of S that we are getting, that quantum mechanics is predicting. And the value of X that we get is this one, 2 root 2. So quantum mechanics, in this setup, quantum mechanics gives the value that we can calculate and also we can measure is 2 root 2. So this is a clear violation of the bound that reality and locality gives. And it is not just violation, it is actually maximally violated because this 2 root 2 is the maximum number. that you can get. So it is a maximum violation. So this shows that the combination of locality and realism is fundamentally incompatible with the prediction of quantum mechanics. Quantum mechanics is fundamentally non-local, and entanglement is an essential character of this, of quantum mechanics. All right. So let's now have a quick update, or like to see the milestones, experimental milestones. So after this initial foundation, theoretical foundation, the first experiment that actually did this Bell inequality test was in 1972. And they got the violation, but of course that was the first attempt. So there was what we now call the loopholes. And then in 1962 we have this famous aspect experiment, followed by the trapped ion Bell test in 2001. Then in 2015 there was this like breakthrough, because in 2015 for the first time 3 independent group validated this Bell violation, and they have done the first time the what we now call the loophole free test. And since then, there was a continuous effort to look for this Bell test in several energy frontier and also like several setup. So we can see that satellite Bell test in 2017, cosmic Bell test in 2018, and in 2024, experiment was performed in 2023, and it was published in 2024, 2 years back. The first evidence of entanglement in top anti-top system. You know, in LHC, in PP collision, there is top anti-top pair production, mostly from the gluon fusion. So Atlas experiments, first time with high significance, statistical significance, they have got the clear evidence of the fact that this T and T bar that are produced are actually entangled for some time. Okay. Okay, so as I said that this year 2015 was a milestone 10 years back. So before 2015, experiments violated the Bell inequality many times, but every test had at least one loopholes. And so for 50 years, so critics could argue that the experimental violation might be explained by loopholes. So these are the 3 experiments that validated this. So what are, very quickly, what are those loopholes? There is these 2 loopholes, locality loopholes and detection loopholes. So in experiment, like we say that there is the 2 qubit A and qubit B. So in experimental setup also, we have to place the entangled qubit in such a distance, and the measurement would be such fast that these 2 points would be causally disconnected. So the first experiment, the first group, they have kept this like 1.3 kilometer in a same university at 2 different lab, and they made such a fast measurement of this trial, which we like theoretically said that they were causally disconnected during this trial. So anyway, so that way they have removed the locality loophole, and also the other loophole was detection loophole. Detection loophole said that the experimental efficiency would be so high that we don't leave any data, because if I leave some data, then the critic will argue that you have selected only the favorable data which actually violates, the unfavorable data which doesn't violate are actually discarded. So that way they have to ensure that efficiency is also very high. So this way they have done the detection like loophole free test. All right, so returning back to entanglement and Bell test at LHC. So in LHC, they have got the clear evidence of entanglement, but the Bell test is not yet done. Because sorry. So in LHC, or in for that matter in any collider, the quark anti-quark pair are produced in hard scattering. So the moment they are produced, this can be thought of as a joint, say QQ bar, as a like 2-qubit system in the framework where the way we are discussing here. So this is a like 2-qubit system. So naturally the density matrix could be of this form, and of course the top cannot be detected. So because of the high mass of the top, it would quickly decay, and the decay and eventually these leptons, lepton L plus and L minus, would eventually reach to the detector. So by measuring these leptons, and this spin information are trickled down to the lepton. That's a good thing, that opportunity they have used, and then they try to reconstruct from this cross section what could be the spin density matrix of this quark anti-quark pair, or TT bar pair. And the marker or the observable that they have studied is actually the trace of this correlation matrix. And this correlation matrix trace can be directly connected with the angle between these leptons that eventually reach to the detector. So after taking average over many such events, and then there are some subtleties, and this D can be estimated. Now, if D is greater than 1/3, then it's a signature of entanglement. If it is less than 1/3, then there could be spin correlations, but those correlations are not quantum correlations; they are classical correlations. Phi is the angle between the charge lepton directions. So T decay to L plus eventually, and T bar decays to L minus. So angle between these two.
You don't detect the neutrinos.
No, no, no.
So this is just the lepton, anti-lepton. You detect
Yes.
intangible.
Yes. Yeah, like not me. I'm just citing. So what Atlas measured is kind of like of the like close to 0.6, which is 5 sigma at 5 sigma. So that was kind of discovery of entanglement is present in this setup. Now the question is, can this also be studied in a DIS setup? Say for example, like say in a setup of EIC. So there are very recent studies last year. People tried to see what would be the correlation matrix or density matrix for EIC setup. In EIC setup, I should have a top, like not top, but heavy quark, anti-quark in the final state. And so if we have a heavy quark, anti-quark in the final state, the key result was, if this photon that is coming in a DIS diagram, if it is longitudinal photon, then this quark anti-quark pair will always exhibit maximal entanglement. So that is something that people got, that if the photon is longitudinal, then this correlation matrix is maximally entangled, and it's a pure state, which is not true for, and it also reaches like optimum value for CH/SH inequality. But if this is a transverse, then it's not the case. For transverse photon, this is a complicated matrix, and it is a mixed state. So that is one result, that theoretical result, that people find intrigued, that this is the case. And these elements are kinetic elements, so they are function of scattering angle, mass of the heavy quarks, etc. And then, so then the idea is the same. By measuring the lepton pair in the decay product, one can extract the spin correlation matrix for the heavy quark pair, and thereby studying the elements and like entanglement and Bell non-locality at EIC. Everything is on like theoretical arguments. Experimental feasibility is actually maybe in 1 or 2 years it could be part of the EIC program, hopefully. Oh, this spin matrix is traditionally the spin matrix that we calculate is in the anarchy basis. So you want me to explain the anarchy basis? No, that I can do, but let me finish. So anarchy basis. So you need. So if you want to study spin, you need basis. So I need to have an orthogonal basis, and the most convenient basis is what people traditionally. So it all starts from this paper. If we see, during COVID time, people thought of having, can we test the entanglement in LHC? And then eventually they got this. So this is the first theoretical. So in this paper and the follow-up paper, so now people use this NRK basis. NRK basis in a way that this K is the direction of the top. N is something. Okay, so if you have proton collision, say gluon, and then you have top. So this is K. N is directly through the board, and then here you have the N R. So that is a basis, and in this basis, these matrix elements are correlation matrices are calculated. So those correlation matrices are in leading order. In leading order, in the final state we have Q and Q bar, and there is no other, say, extra gluon emitted. So it's like a leading order result. So the final state is like exclusive. So in that, in information science language, so we have the full knowledge of the final state. So that is one point. The other point is that there is no unobserved gluon in the final state. Gluon, it's not that there was a gluon and it's not detected. So that these are the character of leading order. But then what happened to NLO? In the NLO, we could have the virtual photons, virtual gluons, and also could be the real gluon emitted in the final state, in addition to quark and anti-quark. Okay, so at NLO, we have this leading order, and then virtual, and also the leading order real emission. But this real emission, if we can't able to detect that in the detector, then we should trace it over. So now, because we are tracing over the gluons, additional gluon, now the density matrix is like kind of reduced density matrix. And there are issues like, is the NLO density matrix IR safe or not? So whatever I am discussing now is not like, it's actually what we are doing. So it's not. So those questions are now there, that if they are IR safe or not. Okay, so what could we?
So you're going to detect some jet with some cuts.
Yes.
Some more momentum cuts or something.
So yeah. So no, of course not. But then in experiment we have cuts, we have region which are not accessible. So those would be part of our ignorance of the knowledge. So that way, it's a very simple model could be, say, a fraction of the total observed sample could be truly exclusive quark anti-quark event, and the smaller fraction could be an unobserved radiation scramble the 2-qubit correlation and make it a kind of noise. So if that very toy kind of model could be thought of that it's like bell-like pure state, and because of this noise it becomes a Wiener state. So if that is the case, then of course because we are bringing a noise here, the maximal entanglement that we saw in the longitudinal case will get down, but it would still violate the CH-SH inequality up to this 0.29, and entanglement will still persist up to 0.66. Okay. The whole problem can also be put in a Lindbergh description, because if that is the case, then the natural expectation is that this block would have a exponential damping, because this Lindbergh description, Lindbergh equation is nothing but the evolution of the rho, maintaining the positivity and trace 1, etc. So that naturally brings suppression factor in front of those coefficients. So can we exactly calculate those suppression factors from the NLO full one loop QCD calculation? So those are the open question. A very preliminary work indicates that this delta gamma could be the non-curves anomalous dimension are actually contributing, not the curves anomalous dimension. Curves anomalous dimension is something responsible for this Sudakov factor double log. They cancel from this normalization of the density matrix. What left is this non-curves anomalous dimension. So what I am saying is something actually like it's like work in progress. So very quick comment on small x. What happened is that the small x. I forget to mention one thing. I think it's worth enough to say that if this it is also now established that if the gluon is a pomeron, multi-gluon singlet state, if it's a pomeron exchange instead of a single gluon, then also this is for longitudinal case, this is maximally entangled. Okay, so general expectation is that because in small x radiation would be dominated by BFKL type of evolution, and BFKL kernel would play a role, and it seems like the decoherence effect would not be that much suppressed because this BFKL is primarily in its leading order spin blind. It doesn't depend on spins much. It mostly deals with momentum. So longitudinal momentum entanglement is probably perturbatively stable at a small x, at least in the leading order. So the final point is whether these studies can be connected with the regular PDF studies, GPD, TMD study that we do. There are very recent work on this direction. In fact, we have also studied this spin in spin orbit entanglement setup, that entanglement negativity can be connected with the gluon helicity PDF. So initially I thought of discussing this here, but then I changed my idea because the composition is mostly students. Okay, so this is my final outlook. So hard scattering process creates entangled partonic state. Those can interact with the medium, and the entanglement can degrade. And studying this evolution may give a new way of looking at this problem of thermalization probably. So there are some questions like how decoherence appear in NLO, how GPDs are connected to quantum correlations, and whether this entanglement are a generic property of QCD dynamics or not. Probably these things would be settled in next couple of years. So that was all. Thank you.
Thank you, Abir. Any question?
Can you explain the last slide?
This one.
No, the last slide you had. Yeah. So what was the message here?
Message
Can you
is,
go over to it through it?
message is that this is not a disconnected discussion. It is the traditional discussion that is the study that we do, like TMD, PDFs, PDF study, Helicity PDF, GPDS, the community that we have. Probably they find these problems interesting because they are directly connected, not very far. That was the message.
This entanglement negativity, your connection to gluon helicity.
So that is something.
Is something that you can explain
Now,
in few words, or
in few words.
why? Yes, how can we see that? Appreciate that.
I can't find any starting point from where I can start.
The gamma longitudinal or transverse from experimental measurements. You said that longitudinally polarized gamma had maximal entanglement and transverse not.
Yes.
But how can you know which one it is?
In textbook DIS, longitudinal gamma. You mean this one?
Yeah, for example.
So longitudinal gamma is giving contribution to this structure function FL.
But you have to observe the Q and Q bar, right? So. So do you know in a particular process, in a particular process whether
experimental setup,
yeah,
if we just try to isolate this particular part with and should not like how to get observable, that would get contribution only from the longitudinal part.
It's not obvious, right?
It's not obvious. Like, so the most yeah, so it's not very obvious. Theory, in theory front, this particular problem in DIS setup or EIC setup, only few studies are there, like 3-4. So it just started.
Yeah, I would like to return to the Atlas measurements on TT bar. Well, let me put my question in the direct way. How robust are the results in terms of measurements of Bell inequality?
Yeah, how robust?
Because you measure, you don't measure the TT bar, you measure the electrons.
Exactly.
And not the neutrinos. So
yes.
how much control do you have on the final results, on the entanglement of TT bar?
Yeah, so as I can give my theoretician view because I'm not like experimentalist, but what they are pretty confident that the spin information that the TT bar has, that actually percolated to nu, because this is the only channel that they have weak channel through W, and because weak interaction gives maximal parity violation. Weak theory is maximally parity violating theory also. So that actually help to reconstruct the spin information through the lepton. And I was actually reading the paper yesterday thoroughly again, the Atlas paper, and they are claiming it's like 100% certainty that nothing is left out. Reconstructing the spins of top from the lepton is actually not ambiguous. It's not ambiguous. It is pretty much here.
I just want to put some note.
I can just want to make one more comment that this is very subtle, because even if the correlations are there, spin correlations are there, there could be, for example, CMS got a number which is less than 0.1 So they have correlations, spin correlations, but they can't claim that it is of quantum origin. So to have a quantum origin threshold bar crossed, it has to be crossed this 1/3. So unless we have a very confidence in these facts that actually they are reconstructing the spins of the top, nobody, and those collaboration can't claim that they are actually getting the entanglement, because anything that any correlation, classical correlation will give non-zero D, but it has to be cross this threshold.
Actually, in Hera, they try to measure they call Shannon entropy. So they measure the Gluon distribution function initial. They get a very inconclusive result. So you can, from Hera, yeah. So they probably looked at their data again. You can check that paper. I think there was a follow-up paper by Dima Kharji. So they are trying to do that in a different way, not in that same atlas type measurement.
How do you pick up the T events? You tag the B?
Yeah, you have to tag with any other
Maybe you can.
Yeah, but how do you know the leptons come from the top? You look for the B, things carrying B. Okay, is that, how do you know?
No, leptons and neutrino is not okay.
Neutrino
but
is not
lepton you can get it. Then
yeah, but how do you know the leptons are coming from the top?
Yeah.
Do you tag
Probably yes, they have done that.
Yeah, we need to exactly see the paper how they have done it. Yes.
Yes.
Yeah, but specifically in this measurement, what they have done, we have to look at. Yeah, that's why I don't want to comment.
So I really have to sit with him, then I can say, I can tell tomorrow.
So any further question?
So you were talking about the TMDs, I mean transverse momentum distributions, PDFs like that.
Transverse.
TMDs, some of
TM.
GPD and TMDs. Okay. So how you, how you know the transverse momentum? I mean, you are getting an entanglement and then you
Okay, so
just
where I left the. See, these structure, these diagrams are in isolation, right? When we calculate in isolation, but in actually they are part of they are part of other things. So, for example, proton, the gluons are coming from this proton in a PDF setup. So here you have this PDFs, GPDs sitting. Here you have TMDs. So the quark anti-quark pair that you are getting has in their production process, we have influence from PDFs, GPDs. these boxes. Okay.
I was saying about the transverse momentum. I mean,
No,
earlier you make a comment that if the photon, let's say for the photon have if longitudinally polarized photon, and
Okay, so-
then the entanglement is maximal.
Oh, so
That's-
this photon which is like in
If-
deep inelastic scattering, you get a
Yes.
photon, virtual photon from the electrons or say muon. So this photon can be resolved in two components, like
Yes.
longitudinal and transverse.
Transverse.
So if I just take the longitudinal part of that photon, then the correlation matrix that we are getting is a pure represent a pure state and maximally entanglement. But that is not the case for the
transverse.
transverse. And if you ask me why, then
mean,
that
no, no,
question is
I
not
am
like
asking,
we are still thinking why.
I mean, I am asking because I mean you have no control over photons transverse or longitudinal.
Yeah, that is what Rishi was
Uh-huh.
saying. That, yeah.
Then you just measure a quark antiquark. Let's say, I mean, it is not measurable, but somehow you get the states, and then you have a measure of entanglement you measured. And if this entanglement is kind of maximal by this parameter or the process, you measure the entanglement, and if this entanglement is somehow maximal, then you can infer that this. I mean, that this gamma, which is basically cause the process is kind of transverse. I mean, other way around. So you measure the entanglement, and then you said that this photon is transverse or longitudinal. Is it?
Oh, that is far away from even this is just started of this initiation have started. What I can understand that you say that by looking at the at some far future we get the entanglement which is maximal, and then we can restrict back that the initial photon having this longitudinal components majorly. So those things I can't even imagine now. So it just like started of looking
Okay.
at that direction, because you see even in at last the Bell test is not done yet. It's just getting a signature of entanglement.
Okay.
Bell non-locality is yet not done. Maybe in few years.
Okay. Sorry. I can ask another question. So one of your slides, you said the unobserved, all gluons are observed, or there should not remain unobserved. I mean, unobserved means?
Unobserved means like in NLO, you could have virtual gluons, so that is emitted and absorbed within the diagram. And then you may have also real gluons emitted, right? In the final state, you will find those gluons. Of course, it would not reach, it would reach, or it would be part of the environment or medium, or in extreme cases, it would trigger a jet, etc. But in the final state, you may have a gluon. Now, this gluon, maybe you will detect or may not be detect, right? It would be outside the cart, etc., or part of that. In that way, if you don't able to resolve that gluon or not able to detect that gluon, but it was there originally, right? So it was a three body system in the final state. Now to me or to us, it is a reduced to two body final state. So a larger density matrix is now reduced to a smaller density matrix. So that's why I was saying that if we can't able to detect that final state gluons, the density matrix is reduced.
Basically, the detector acceptance, you don't have full acceptance, you may not get that.
Yes, exactly.
We have plenty of time.
Okay, so yeah, thank you, Raktim, for
Okay,
this
thank you.
interesting talk. And today we don't have any speaker, but we request all the students to talk to our